Every single AI model you've ever interacted with was built on a classical computer. Every chatbot reply, every generated picture, every recommendation engine, every fraud detection tool, every drug candidate that AI helped uncover, all of it ran on chips that process information as ones and zeros, the same basic architecture that has driven computing since the 1940s. And that architecture is now starting to run into walls that adding more transistors or boosting clock speed can no longer push through. The people building the next wave of AI understand this, which is why some of the biggest money and sharpest minds in computing are wagering that the path beyond those walls leads straight through quantum physics. The outcome of that bet is the field of quantum AI, and the particular hardware it's producing doesn't yet have a widely accepted name, but it generally refers to systems that combine quantum processors and classical processors on a single platform to tackle problems neither could solve alone. This video will lay out exactly how that works, what it can genuinely accomplish today versus what's still years off, and why the honest answer to whether this spells the end of classical AI is both messier and more fascinating than either the hype or the skepticism would suggest. To understand the problem quantum AI is trying to solve, you first need to understand why classical AI is bumping up against limits that aren't merely engineering hurdles, but mathematical ones. Modern large language models and deep learning systems function by tuning billions of parameters across neural networks, optimizing them to reduce prediction error through a process known as gradient descent. Training a large modern AI model eats up weeks of time across clusters of thousands of specialized graphics processing units, consuming electricity budgets that can reach tens of millions of dollars for a single training run. The energy demands of AI infrastructure have become one of the defining infrastructure stories of the mid-2020s, with data centers projected to consume a share of global electricity that's genuinely alarming given current growth trends. And the gains from scaling these models, simply making them bigger and feeding them more data, have been showing signs of leveling off in ways the research community has openly discussed over the past year. Hit like right now, because the specific mathematical snag buried inside AI training is exactly what quantum computing seems almost built to attack. The heart of the challenge is optimization. Finding the best possible combination among billions of numerical parameters across an enormously complex landscape of possible configurations is a combinatorial problem that grows exponentially with the number of variables involved. Classical computers cope with this through approximation, using gradient descent to land on solutions that are good enough rather than truly optimal, because finding the actual global optimum in a space this vast is computationally impossible for classical hardware. This isn't a flaw in how AI training is currently done, it's a fundamental mathematical ceiling on the classical approach, and it shows up as issues like models getting trapped in local optima, needing massive compute just to escape, or simply never settling on the best possible set of weights. Quantum computers tackle optimization from a completely different angle. Rather than checking possible solutions one at a time and inching downhill toward a local minimum, a quantum system can use superposition to explore a huge number of possible configurations at once, then use interference, the constructive and destructive interaction of quantum probability waves, to boost the paths heading toward better solutions and dampen the ones heading toward worse outcomes. The theoretical speedup this offers for certain optimization problems isn't linear or quadratic. For the right class of problem, it's exponential, meaning a task that would take a classical computer longer than the lifetime of the universe could theoretically be solved in minutes. The intuition behind why interference helps so much with optimization is worth sitting with, because it's one of those ideas that seems baffling until it suddenly makes sense. When you try to find the lowest point in a complicated landscape of possible solutions using a classical computer, you have to check paths one by one, always risking getting stuck in a valley that isn't actually the deepest. A quantum system running the right algorithm instead sets up quantum waves that travel across every path at once. Where paths lead to bad solutions, the waves cancel each other out through destructive interference, much like noise-canceling headphones subtracting unwanted sound. Where paths lead toward better solutions, the waves reinforce one another through constructive interference, growing stronger and more likely. Measuring the system then tends to return the better solutions, steered by this quantum wave structure that has no parallel in classical computing. Subscribe right now if you want to know the exact moment this stopped being theory and turned into actual hardware. In October 2025, Google pulled off something the quantum computing field had been working toward for years. Using its Willow quantum chip and an algorithm called quantum echoes, Google showed a 13,000 times speedup over the Frontier supercomputer, one of the most powerful classical machines currently running, on a specific physics simulation task. That number is dramatic enough that it needs immediate context. The task was chosen specifically to highlight quantum properties rather than to address a direct commercial use case, and the broader physics community was quick to note that this shouldn't be read as a general-purpose speed-up for everyday computing. But what made the Willow result truly significant was the error correction performance underneath it. Google showed that as the system scaled up to larger logical qubit counts, the error rate actually dropped instead of rising, achieving what researchers call below-threshold error correction, the mathematical prerequisite for building fault-tolerant quantum computers reliable enough to handle real-world problems. Around the same time, IBM was pursuing a parallel route with its Nighthawk processor, a 120-qubit system linked by 218 upgraded couplers, capable of running circuits up to 30% more complex than IBM's previous generation. IBM has publicly stated it's aiming for verified quantum advantage by the end of 2026, and in this context, advantage means outperforming the best classical methods on a commercially relevant problem, not one designed purely to showcase quantum properties. The roadmap stretches to fault-tolerant systems by 2029, with Nighthawk scaling toward 15,000 entangling operations and over 1,000 qubits by 2028. IBM also unveiled a companion chip called Quantum Loon, built specifically to test the hardware infrastructure needed for error correction at scale. These milestones are arriving in a field where research intensity has been ramping up sharply. The number of peer-reviewed papers on quantum error correction more than tripled between 2024 and 2025 alone, and the surrounding engineering infrastructure, cryogenic control electronics, quantum error decoding systems, and hybrid classical quantum software stacks has been maturing right alongside the processors themselves. If you're starting to see why this video's title says this could be the end of classical AI, go ahead and smash that subscribe button, because the next section breaks down how hybrid chips actually work in practice. Here's what's really happening inside a quantum AI hybrid system, explained without requiring a physics degree. The classical and quantum processors in a hybrid system aren't swappable. They're deeply complementary, each handed the parts of a problem it's best suited for. The classical side, running on GPUs, CPUs, or AI accelerators like TPUs, manages data ingestion, pre-processing, large matrix operations, inference, and the overall coordination of the workflow. That's what classical hardware excels at. The quantum side handles a narrower set of tasks where it offers real advantage: high-dimensional optimization, sampling from complex probability distributions, and simulating quantum mechanical systems that classical hardware simply can't model accurately at scale. In a practical hybrid workflow, this plays out as follows. A classical system sets up a problem, encodes the relevant parts into a quantum processor through a process called state preparation, runs a quantum algorithm on the quantum hardware, measures the output, and feeds those results back to the classical system to steer the next round of computation. This cycle repeats many times in what's known as a variational quantum circuit, adjusted by the classical processor between rounds to refine the result. The resulting setup is called a variational quantum eigensolver, or VQE, when used to find the lowest energy states of molecular systems, and the quantum approximate optimization algorithm, or QAOA, when applied to combinatorial problems like scheduling, routing, and resource allocation. The reason these hybrid approaches dominate right now rather than fully quantum methods is that today's quantum processors, what the field calls noisy intermediate-scale quantum devices, or NISQ machines, are capable of meaningful computation, but not yet reliable enough to run long quantum circuits without piling up errors that wreck the result. By limiting the quantum processor to the specific subroutines where quantum advantage actually exists, and keeping everything else classical, hybrid systems squeeze quantum value out of hardware that isn't yet fault-tolerant, which is exactly the hardware that exists today. Here's a real-world example that's already left the lab and entered actual financial infrastructure. HSBC partnered with IBM Quantum to test whether quantum machine learning could sharpen financial prediction models for market behavior and bond trading data. The team used quantum kernel methods, a technique that maps financial data into a high-dimensional quantum state space where classical machine learning algorithms struggle to spot patterns, and compared the results against classical machine learning approaches on the same data. The quantum-assisted models cut down prediction errors and improved accuracy in certain scenarios, showing that quantum AI isn't just a future promise, but something a major global bank is already testing against its real operational data. The quantum kernel approach is worth unpacking a bit more, since it sits at the core of why quantum systems can be classical ones on specific machine learning tasks. Kernel methods in machine learning work by measuring how similar data points are within a high-dimensional space, where complex patterns invisible in the raw data become linearly separable and far easier to classify. The catch is that computing similarities in extremely high-dimensional spaces is computationally costly for classical hardware, since the required resources grow exponentially with the number of dimensions. A quantum system, by contrast, can encode data into a quantum state that naturally exists within an exponentially large Hilbert space and compute similarities using quantum interference, reaching that high-dimensional structure without paying the exponential classical cost. This isn't a trick or workaround. It's a genuine structural advantage built into how quantum information naturally behaves. The drug discovery application deserves extra attention since it represents the clearest near-term path for quantum AI to deliver measurable economic value in ways that touch ordinary people. Pharmaceutical companies spend billions of dollars and over a decade on average to take a new drug from initial discovery to market approval. A significant chunk of that cost stems from how hard it is to predict how candidate molecules will behave when interacting with biological targets, which requires simulating the quantum mechanical behavior of electrons in molecules with a level of precision classical computers fundamentally cannot reach for large, complex molecules. This isn't a computational bottleneck that faster classical hardware will eventually solve. It's a fundamental constraint rooted in the exponential scaling of the underlying quantum mechanical equations. A sufficiently powerful quantum processor running a variational quantum eigensolver algorithm could simulate these molecular interactions precisely enough to reliably flag promising drug candidates before costly lab synthesis and testing even begin, potentially compressing years of trial and error into weeks of quantum simulation. Several major pharmaceutical companies, including Roche, Pfizer, and Boehringer Ingelheim, have been running quantum chemistry programs alongside quantum hardware companies, testing whether quantum circuits can already produce useful molecular simulation results on today's NISQ hardware. And the results emerging from these early programs are one of the main reasons investment in quantum AI hardware keeps accelerating instead of slowing down, despite the ongoing engineering hurdles. Go ahead and hit that like button, because what's coming next is the question the industry is still actively wrestling with: the honest timeline for when this becomes transformative at scale. Not everyone agrees on when quantum AI hybrid systems will become capable enough to make a real difference for mainstream AI workloads. Jensen Huang, NVIDIA's CEO, whose graphics processing units currently power the vast majority of AI training infrastructure worldwide, has publicly estimated that genuinely useful fault-tolerant quantum computing is still 15 to 30 years away. His view carries real weight, not just because of NVIDIA's central role in today's AI industry, but because he points to concrete technical obstacles, chiefly the enormous engineering challenge of building the error correction infrastructure that fault-tolerant systems demand at scale. One of the most serious obstacles that often gets glossed over in popular coverage of quantum AI is the data encoding problem. For a quantum processor to offer a speed-up on a machine learning task, it first has to load the relevant data from the classical world into a quantum state, a process requiring hardware called quantum random access memory, or QRAM. Building a QRAM capable of loading large data sets fast enough to preserve a practical quantum speedup remains one of the most significant open engineering challenges in the whole field. If encoding data into the quantum processor takes as long as, or longer than, the speedup the quantum computation provides, the hybrid system loses its edge before the quantum processor even starts running. This is a real constraint, not a theoretical objection, and it's part of why near-term quantum advantages are expected to show up first in problems involving small, carefully structured data sets, rather than the massive training sets modern AI depends on. Google and IBM, meanwhile, are targeting commercially relevant quantum advantage within the next 2 to 4 years, with fault-tolerant systems arriving by the end of this decade. IonQ, working with trapped ion technology rather than superconducting qubits, demonstrated a 12% performance edge over classical supercomputers in medical device simulation in early 2025, a smaller but commercially focused result pointing toward near-term practical applications in very specific domains. The DARPA Quantum Benchmarking Initiative is trying to bring independent, standardized evaluation to these competing claims, because the quantum field has learned the hard way, from past episodes of premature announcements, that clear external verification of progress is essential to the community's credibility. The honest takeaway from examining all of this closely is that the answer to when quantum AI hybrid chips become transformative depends heavily on which specific problem you're asking about. For certain optimization problems in logistics, portfolio management, and drug molecular energy simulation, quantum subroutines running inside hybrid systems are already delivering measurable improvements in experimental deployments right now, in 2026. For the kind of general-purpose, large language model training that powers the AI products most consumers use every day, the hardware and algorithms needed to deliver a genuine quantum speedup simply don't exist yet, and the realistic timeline for when they might remains genuinely uncertain, with serious, technically credible people disagreeing by roughly 5 to 10 years. What isn't uncertain is the direction things are heading. McKinsey published an analysis pointing out something important about the quantum AI relationship that tends to get lost in all the excitement about quantum hardware. The relationship between quantum computing and AI runs both ways at once. Quantum computing accelerates AI by offering exponential speedups on the optimization and simulation problems classical AI struggles with. But AI also accelerates quantum computing, because machine learning algorithms are now being applied to the problems of quantum hardware itself, optimizing error correction codes, modeling noise in qubit systems, and automatically calibrating the control pulses that manipulate qubits with the precision high-fidelity operations require. These two technologies aren't simply replacing one another, they're actively improving each other in tandem, which is part of why the timeline to meaningful quantum AI capability might end up shorter than a straight-line extrapolation from today's hardware would suggest. A concrete example of AI accelerating quantum hardware is worth spelling out. The control electronics that run a quantum processor have to generate extremely precise microwave pulses to manipulate qubit states and entangle them without introducing errors. Traditionally, tuning these pulses has been an expert manual job requiring specialized physicists to spend days fine-tuning a single processor. Machine learning systems trained on a processor's noise characteristics and qubit response patterns are now automating this calibration, shrinking a days-long manual process down to hours of automated optimization, directly boosting qubit fidelity and enabling faster iteration on hardware improvements. AI isn't just benefiting from quantum computing, it's actively helping make quantum computing more capable, faster. The architecture of future AI data centers is already being planned, with this convergence in mind. The model that leading researchers and infrastructure companies are converging on isn't classical hardware being replaced by quantum hardware, but an augmentation, where quantum processors join GPU clusters and specialized AI accelerators as co-processors, each handling the workloads where its design delivers the most value. A quantum processor tackling high-dimensional optimization, while a GPU array handles large matrix multiplications, and a classical CPU manages data flow and coordination. That's the data center architecture serious technical institutions are building toward, not a world where classical computing suddenly becomes obsolete. The idea that this is the end of classical AI is therefore the wrong way to frame what's actually happening. Classical AI isn't ending, it's gaining a fundamentally new partner capable of handling the specific categories of problems that have historically bottlenecked how far classical AI can go. The limitations quantum AI is designed to address are real, and the evidence that quantum hardware can tackle some of them is no longer purely theoretical. But the timeline is longer than the most breathless coverage suggests. The problems quantum AI solves first are narrower than general-purpose AI acceleration, and the near-term future is firmly hybrid rather than purely quantum. The more accurate way to understand this moment is that we're watching the early stages of computing's next major architectural shift, the kind that only comes around a few times in a generation. The shift from vacuum tubes to transistors, from mainframes to personal computers, from single-core to multi-core processors, from CPUs to GPUs for AI training. Each of these transitions looked gradual and uncertain from inside the moment, and obvious in hindsight from outside it. In every case, the people dismissing the new architecture as impractical were making technically accurate observations about the current generation of hardware. Vacuum tube computers really were more reliable than early transistors. Early GPUs really were clumsy tools for AI researchers before the software ecosystem matured around them. The critics were right about the present and wrong about the trajectory, because architectural shifts compound their gains in ways that linear extrapolation from current limitations consistently underestimates. Quantum AI hybrid systems are the next shift in that lineage, and how well you understand how they work and what they can actually do right now will determine whether you're prepared for the world they create or caught off guard by it. The organizations building quantum AI literacy today, running experimental hybrid workflows, training teams in quantum algorithms alongside classical deep learning, and forging partnerships with hardware providers, are building a 3 to 5 year head start in a technology the wider industry will scramble to adopt once the fault-tolerant milestone arrives. The history of every major computing transition shows that this kind of head start compounds into a structural advantage that latecomers find very hard to close. Hit that like button, subscribe to this channel, and turn on notifications, because this field is moving faster than almost anything else in technology right now, and the next benchmark, the next hardware announcement, the next demonstration of real-world quantum AI advantage could come from any direction, any week. You deserve to understand it when it does.